Yeah, it's my great pleasure to be here today representing the Star Formation ISM Galactic Winds Working Group to share some of our recent progress. Before we begin, yes, there are always people who actually made all these things possible. So these are faces of our working group members. In addition, Greg, Rachel, and Jan have been participating our working group activities, who were instrumental actually in connecting our work to the entire collaboration. So as Greg outlined earlier, our collaboration is structured around several key tasks, and our group's focus is on this critical component, developing the physics-based subgrid model for cosmological simulations. Specifically, what we are doing is for star formation and stellar feedback. And to do this, we use kind of the multi-scale strategy with an iterative kind of the development cycle. So we first use this kind of the high resolution local simulations that resolve the detailed physics of the ISM to calibrate our proposed models. So we then validate them in this kind of the global galaxy simulations and also develop some prototype implementations. Then we work with the cosmological modeling working group to deploy these models into large-scale cosmological simulations. Then finally, we assess the result to identify the areas for the next round of the improvement. So this is actually some iterative cycle, and I would say that we are kind of almost completing the first iteration. So over the first LTU period, our working group actually made excellent progress in all four of these areas, both star formation and the galactic wind side. And today I'll give a brief overview of our major achievements. Then I will focus on some two very recent progress. First, the successful implementation of our new star formation model, PRFM. And second, our new baseline local simulations, including cosmology feedback. So first, overview and overview for the goals and progress. So to set the stage, I want to basically highlight a fundamental issue with the traditional subgrid models. Most traditional approaches depend heavily on the density, gas density measured in simulations. So this dependency actually appears at every step. First, the density is used to set an effective pressure, mostly for numerical stability. Then density determines the star formation rate through density-dependent timescale and efficiency. Finally, this star formation rate is used to model galactic winds, where these wind properties are actually often tied to the global galaxy and halo information. And typically, these models are empirically calibrated to match certain observations, which is another weakness. But no matter how good this model is, if the density from the simulation is unreliable, all of its predictions are basically compromised. And unfortunately, the density of star-forming gas is unreliable in most cosmological simulations. Some simple estimation of spatial resolution, like this, basically implies that the 10 to the 5 solar mass resolution is required to just begin resolving the disk scale height, which is about a few hundred parsec scale, in the neutral ISM. So even in the next generation cosmological simulations, this is not really feasible in the large volume simulations. As you can see, there are lots of the kind of the current state-of-the-art simulations. They are mostly this kind of the rhythm is basically lacking. So therefore, our primary goal is actually to develop some new models that use variables that are both more physically motivated and also robustly measurable in low resolution simulations. And this model should also reproduce some physical behaviors at much coarser resolution than these high resolution models. So for star formation and the ISM, we are implementing the pressure-regulated, feedback-modulated star formation theory, PRFM in short. This theory basically proposes a direct physical link between the star formation rate and the total pressure. In the disk, because the stellar feedback is the main source of the energy and the momentum in the ISM that sets the total pressure. And furthermore, this total pressure must balance with the gravitational weight, which can be written in this way, that actually can be calculated analytically using some surface densities that are more reliably measurable in the low resolution simulations. And also, these are also measurable in the observations. So as you can see on the right figure, this theoretical prediction agrees very well with observations of nearby star-forming galaxies. So then what we need to do is actually we need to calibrate those relations, which is basically characterized by this epsilon parameter. So we use a high-resolution local simulations that include the ISM physics and stellar feedback explicitly to directly measure the relationship between the star formation rate surface density and each component of the pressure that can actually provide the calibration of this so-called feedback yield for the thermal component and the turbulent component as a function of basically this weight parameter, or also as a function of the metallicity. So these are examples using two different generations of Tigris simulation suites, varying degree of the physics complexity. We then actually validate this PRFM framework in global galaxy simulations. So the plot shown on the right here is basically showing the pressure and the star formation rate relation, basically our PRFM model, which works more kind of coherently across or diverse range of the galaxy types, which represented as a different symbol there, from star-forming disks to early type galaxies. In contrast, this traditional density-based relation here only actually work reasonably well for the Milky Way-like galaxies, where it is actually calibrated. So we are now extending this kind of validation work using dwarf galaxies with more complex and messier structure, and also mergers. So finally, the PRFM model is actually now being deployed in cosmological simulations. So the early deployment result of the PRFM motivated prescription were presented in the Jan's paper submitted earlier this year. But this still uses gas density-based star formation rule with some steeper slope that is more motivated by the PRFM prediction, and Tigris calibrated EOS. So we are actually continuing to work closely with the Cosmological Modeling Working Group on the full deployment of the PRFM implementation that I will describe shortly. So moving on to galactic wind side, our approach is again to start with local physics. So many existing wind models in cosmological simulations use global galaxy or halo properties to set the wind parameters. However, the wind launching is actually a local process. So the observed global correlation should be an outcome, not an input. So we use Tigris simulations like this to characterize the multi-phase properties of winds, right where the winds are launched using this velocity and temperature PDF for the mass flux and the energy flux. And we can also obtain this qualitatively similar characterizations using some global galaxy simulations, as shown from this Ulrich's work. But launching winds is only half the battle. We also need to evolve them correctly in low-resolution simulations. This is actually challenging for two reasons. The high specific energy wind, hot outflows, are actually usually very low density and then poorly resolved in the Lagrangian simulations, where the mass resolution is constant. And the interaction between the hot and cold phase is completely unresolved. And to solve this, Matthew and Drummond have led efforts to develop this Arkenstone model. So Arkenstone hot is a novel refinement method that increases the resolution for high specific energy winds. As you can see here, this is basically a radial profile of the velocity in the solid line. Without Arkenstone, if we just launch the same kind of high specific energy winds, it doesn't accelerate as it needed to be. But with the Arkenstone refinement scheme, you can actually accelerate and pass it through the sonic transition point correctly. So the first deployment of this Arkenstone hot in a cosmological setting is now complete, as shown in a recent paper led by Jake. These high specific energy winds alone can actually regulate galaxy growth through this preventative feedback by heating the CGM and stopping accretion. And this has major consequences for the CGM properties and many secondary properties, which we are just beginning to explore. And the next generation model, Arkenstone 4, which handles hot-cold interaction through the subgrid model based on a turbulent mixing layer theory, which is now ready for cosmological testing. So those were some of our major achievements so far, and now for the next few minutes, I'll describe the implementation of our new star formation subgrid model in more detail. So as a reminder, the core problem we want to tackle is this unreliable nature of the density where stars form in the simulations, which compromises all these traditional model predictions. So we can directly actually demonstrate this problem by comparing these measured quantities from the simulation and to the values predicted by this dynamical equilibrium. If the scale height is reserved, they should match on average, meaning that this ratio plot for the pressure and mid-plane density and the scale height should rise near this unity line shown as a black line. And as I argued earlier, 10 to the 5 solar mass resolution gives kind of marginally reserved results. So their distribution is actually centered around this unity line. But resolution gets poorer. The measured pressure and the density are underestimated because the scale height is overestimated. So what can we do in this case? In the proposed PRFM theory, we want to use the total pressure or the weight with calibrated feedback yield. Even in this unreserved case, the weight can be correctly calculated analytically using surface densities that can be more reliably measured in the low resolution simulations. So by replacing this pressure with the weight, and we basically rearranging all these equations, what we can get is basically this depletion time with this calibrated coefficient and this dynamical time, which is analytically written in the form, expressed in the form with the variable that is more reliably measurable. So I tried to summarize this method more schematically because I don't want to actually fill the slide with all these equations. So because the gas density of star-forming gas is unreliable, we basically bypass this density entirely and just rather measuring the surface densities around the cell. And then we use this to compute the scale height and the weight and use the PRFM logic to get the star formation rate surface density. And that gives us the depletion time. We can use that to estimate the star formation rate. What we actually do is we first calculate the equilibrium scale height, and then use this kind of formula to get the density, weight, and then we get the effective velocity dispersion, which actually was used to get the scale height. So this is actually iterative solve. Usually the one or two or three iteration are enough for convergence. But in the reserved case, if we can actually afford the resolution, we can actually take simpler steps. So similar steps, but we can directly use the density. In this case, we don't really need the iteration. But another thing to consider in this case is that there are now many kind of low density star-forming gas away from the middle plane. So the global depletion time estimate cannot be directly used as a local depletion time for individual gas particle. But we can use the global depletion time estimate as a constraint to calculate the correct renormalization for the local depletion time. But this can be done analytically. So this basically forms this basically forms two types of our PRFM implementation, and then we basically use these global simulations to test that. So first, PRFM resolved. We basically apply this method for all resolutions, no matter whether they are actually resolved or not. And at the 10 to the 5 solar mass resolution, this model actually reproduced the target Tigris relation, the pressure and stop motion relation, nicely. But if you go to the lower resolution, 10 to the 7 solar mass, it is off from the relation, but also more importantly, their ranges are shifted down to the lower pressure region, because the pressure is underestimated if you use the pressure based on the density. And then this bottom right panel shows the consequence. Basically, they are not, the step formation rate history are not converged with respect to the resolution. In contrast, when we apply this PRFM unresolved implementation, we can recover this target relation for all resolution with consistent range. So especially their stop formation rate weighted distribution are pretty similar. And then now the x-axis is weight, not the pressure. Then this global stop formation rate history are all pretty well converged, modulo this kind of the early peak that is mostly introduced by the initial condition mismatch. But we are pretty happy with these results. Finally, let's compare this PRFM to the TNG model. There are just basically two key takeaways here. As you can immediately see that the TNG model predicts much lower stop formation rate at a given pressure. And especially, it's more so for the high pressure region. And second, just like our resolved PRFM, it is strongly resolution dependent. So I would say this clearly demonstrates the robustness of our new PRFM implementation and opens up some exciting new opportunities, as this new prediction are pretty different from the classical prediction. And then finally, I'm going to explain some of our new effort to improve our baseline local simulations, which now include the cosine wave feedback. And this work has done in collaboration with many former and current postdocs and students at Princeton outside LTU. In particular, Lucia Amilota played an instrumental role in implementing the cosine wave physics. So this new simulation framework is called Tigris++ for obvious reasons. It combines all the ISM physics we had in the Tigris with a two-moment cosine wave transport module in Athena++. And in this, now I'm gonna play this movie multiple times. And in this movie, basically we will show slices of all these different physical properties within the torque box with 1 kiloparsec in the horizontal direction and then 8 kiloparsec in the vertical direction. First, you can see these first two panels, density and the temperature. And clearly, it shows basically dynamic, highly dynamic and multi-phase ISM, together with very strong multi-phase outflow launched from the disk. And now, focusing on these final 4 panels, those are pressures. You can immediately see that the cosine wave pressure builds up pretty quickly and saturates to the near equipartition level compared to the turbulent and the thermal pressure. And finally, I'd like to draw your attention in this panel, which shows the cosine wave scattering rate that varies many orders of magnitude throughout the domain. And this spatially varying cosine wave scattering rate is the key innovation in our modeling approach. In many existing cosine wave CRMHD simulations, scattering rate or equivalently cosine wave diffusion coefficient is spatially constant. And the results are pretty sensitive to the adopted value of the cosine wave diffusion coefficient. But in our model, we set this cosine wave scattering rate self-consistently based on this plasma theory, the self-confinement framework, assuming balance between the streaming instability growth rate and the wave damping rates. And we consider these 2 different wave damping rates. Basically, in the dense neutral gas near the middle plane, this ion neutral damping is very efficient and leading to very small scattering rate, almost dark here, that makes a very rapid Cosine ray diffusion. However, in the ionized gas above the disk region, the scattering nonlinear Landau damping sets the scattering rate in a moderate value, like 10 to the minus 28 or 27. That basically means that gas and Cosine ray are strongly coupled there, and that the Cosine ray transport in this region is dynamically controlled by advection and the streaming. And this creates basically this characteristic two-zone profile, the near uniform mid-plane Cosine ray pressure profile with dynamically controlled pressure profile decreasing outward. Yeah. So what this actually means is the Cosine ray pressure is, even though their pressure value is almost equipartition with other component, the Cosine rays do not really actually add additional pressure support because it's uniform. So that doesn't actually change the star formation rate. For the galactic winds, however, Cosine ray makes a significant difference. This space-time diagram shows the horizontally averaged mass flux of the warm and cold outflows. Shows that basically this CR-MHD model has a stronger and more sustained warm and cold outflows compared to the MHD run. And their mass flux at around a few kiloparsec away from the disk are about a factor of 2 to 3 higher than the MHD one. And this is not actually due to the change in the wind launching, but actually driven by more gentle acceleration from the Cosine ray pressure gradient in the outskirts of the disk. So what that means for our subgrid models, what does this actually mean for our subgrid model? For this particular simulation representing solar neighborhood, basically we show that Cosine rays don't change the star formation rates, and also it doesn't change how galactic winds are launched. But they do change how galactic winds propagate. So we will run more simulations with varying environment to confirm this. But if this holds more widely, this means the next challenge may not be recalibrating our current star formation and wind launching model, but rather including this Cosine ray effect in the CGM more larger scale. Perhaps maybe we need a future Arkenstone Cosine ray. Okay, here's a summary, which I will now read through. But main takeaway is that we developed and deployed new star formation, ISM, and galactic wind models for cosmological simulations, which are physically motivated and also work more robustly. And this closed the loop of first development cycle, which we will keep improving. Putting this all together, maybe the goal of running LTU's flagship cosmological simulations with new subgrid models is now within reach. Yeah, now let's turn to Ulrich. Yeah. Give me.
Okay. Yeah, can everybody hear me okay? Sounds good. All right, so let's move on. Chang-Goo found a perfect stopping point here because that's exactly what we're going to talk about in the next half hour. So it's like our plans for LTU flagship and things that we can do now while working towards that goal. So I want to give you a brief outline about this. So I want to talk a little bit about a project that's relatively young. So we have started this 6 months ago at the Princeton meeting. I labeled it for the time being, LTU cluster flagship. So that's something I've taken charge of. And I want to walk you through this a little bit in the next couple minutes. Talk about the initial conditions, the simulations we've run, the preliminary results, and the things that I would do differently if I could start over back 6 months ago. I think that's an important point because that's always something in these big collaborations where we have to be very careful to improve on what we've already messed up. And then I want to talk about some of the plans that Volker and I had and other people in the cosmological modeling group had regarding LTU multi-zoom flagship, which is a different branch of LTU flagship. So let me talk about very briefly about the initial conditions generations for cosmological simulations to begin with. So we know the initial conditions for this. That's that. It's the CMB. So we're basically done, right? So what do you need in a baseline cosmological simulation? I'm just saying this because maybe not everybody has done a cosmological simulation in their life. So you can imprint the fluctuations that we get from the CMB onto a meta-power spectrum and basically move these modes in K-space and forward develop your simulation. The twist in the first project that we're gonna do is we're not gonna. You get a random large scale structure in these simulations, which is nice, but sometimes not ultimately the thing you want to do when you know that you have constraints on the power spectrum from the large scales. So we teamed up with Borg and used their constrained initial conditions to get a better grasp on specific objects that we can simulate. And that turns out to work actually quite nicely, and that's exactly where we arrive at the simulation set for LTU cluster flagship. So we call this constraining coma. And the project idea and the project design here was, first of all, to do something impactful. And when we say impactful, we mean do something impactful for theory and observation at the same time. So we wanted to do something that can improve our theoretical understanding, but also be important for like cross-validation against observational data sets. And we wanted it to be scalable. And when I say scalable, I mean we wanted it to be scalable in two ways. First of all, we wanted to be scalable as a project, which means we can like produce lots of data projects that's going to be useful for the public astronomy community to use. And second, we wanted it to be scalable between the working groups. And that's why we had started out 6 months ago in Princeton by just teaming up between the cosmological modeling group and Borg. That's two, which is already a good start. There's obviously the hope that more people, including the star formation ISM group with the PRFM concepts and the black hole group with the different AGN feedback models, can join this effort to some degree. So what have we done so far? We've ran 50 different constrained simulations of coma provided by the white noise fields from Borg at 256 cubed resolution. So the parent is quite low resolution. It's a 256 cube dark matter simulation. The zoom is like okay resolution for a galaxy formation simulation, poor resolution for galaxy formation simulation, very good resolution for galaxy cluster formation simulation is something to keep in mind. So we are currently at 8 times 10 to the 7 solar masses in dark matter and 1.6 times 10 to the 7 solar masses in baryons. So this is fully coupled, not fully coupled in the Borg pipeline yet, but to be fully coupled with the Borg pipeline and the initial conditions generated that I wrote for this that heavily relies on music, which has been kindly provided to the community by Oliver Hahn and Tom Abel in 2011. And we forward modeled these 50 cluster analogs with the TNG model in the moving mesh coda repo. And this is completed this step. So we have 50 simulations now of galaxy clusters that we didn't have 6 months ago. And we also have the hope that they represent coma to a reasonable degree. And obviously, the first thing to do is to compare to common galaxy cluster observables to test the robustness of these ICs by also having the complexity of a state-of-the-art galaxy formation model. So that's actually the first one that I ever did of these. I dug that out for that. It's just like they look nice, galaxy cluster simulations. So that's the dark matter. That's the gas. So they exist. And yeah, that's generally how they look like. We have them also at higher resolution. at least in the dark matter. Some of them completed. And to my big frustration, they look exactly the same at higher resolution in the dark matter, right? This is like, I mentioned this in some of the meetings, that to my big frustration, galaxy cluster zooms always look the same, regardless the resolution. Anyway, so let's move to the preliminary results of this first simulation endeavor that we outlined during the time since the last LTU meeting. So the first question is, how do we quantify that this is coma? So you have, if you do a constraint simulation like my friends in Borg are doing, there's two things that are very important for this, like where is the cluster placed on the sky and what mass does this cluster have, because the mass of coma is quite well constrained. So we do play the opposite game. We look at, like, if we would think about like any galaxy cluster, and I would give you the exercise, you should do the exercise to tell me whether that is coma or not. One of the things that people would look at is Compton Y and X-ray emission from the hot gas. So we play the opposite game, and we try to find cluster matches in Compton Y and X-ray to then determine whether they're actually good fits compared to like what their mass prediction is. To bring everybody on the same page about Compton Y, so this is the first time I ever made a Compton Y map. So Compton Y parameters, Compton upscattering of the CMB photons, the thermal plasma, and you can actually compute this as a electron pressure line integral. So you have to think about how to compute this line integral. There's different methods of like how to get that. We tested several of them, and they basically give us a robust result. For the X-ray, it's a little bit more complicated already because you have the hot cluster atmosphere that emits black body radiation, and you have actually, from thermal Bremsstrahlung emission, approximately you get T to the power of 1/2 and the electron number density squared. That's just thermal Bremsstrahlung emission. And we're going to talk about the caveat that introduces, because we lose some of the emission that comes from the iron lines, which I fixed yesterday evening, but I still need to do the maps for these. So let's look how they look like. I made a short movie of like all the 50 clusters we have in X-ray and in Compton Y. And yeah, you see here some numbers running through it. It's like typical 10 to the 15 solar mass clusters. Some of them are maybe a little bit less massive. The lowest mass cluster is around 8 times 10 to the 14 solar masses over age, and the most massive one is almost 2 times 10 to the 15 solar masses over age. But yeah, this is where we're at. And the first thing you can see is in all of these simulations, you get this somewhat large-scale alignment, which is typical for coma when you see a coma cluster in the X-rays. And you will also see in a lot of them that there is a companion somewhere at the virial radius, which is also an imprint of the fact that we took the large-scale structure around coma into account while simulating these. So we almost, in all of these, get a companion that just sits roughly at R200 here. So this gives us some confidence that we, at least from the Borg pipeline, picked the right cluster. It's already promising. So then we can compute the actual X-ray radial profiles. So this is the green lines here. So we did this for all 50 clusters. And we compared to the eROSITA data from Eugene Kurasov's paper from 2021. And it's, from the observations, quite complicated to actually arrive at the point of these yellow dots, because they had a very clever technique of subtracting out that background. But if we subtract that background, we actually match these surprisingly well over almost 2 orders of magnitude in radius, which is already quite promising. But we scatter a little bit here in the center, right? So there's like 2 decks or something like this, right, between the lowest line and the highest placed line. So this one seems to be somewhat of an outlier to the top, but generally speaking, we tend to underestimate the X-ray signature in the center. So there's reasons for this, why we deviate in the center a little bit more than in the outskirts. Most importantly, it's like cluster center is very dynamic, right? First of all, your BCG is very massive, that shifts around a lot. There's AGN feedback driving turbulence. So it's not necessarily clear that, you know, we don't necessarily expect that to be very tight here. But one of the reasons that could be a culprit here for why we underestimate this is because we miss some of the emission, because we only computed the Bremsstrahlung emission. So that's something we're actively working on. When we look at the Compton Y profiles for these clusters and compare the data of Planck for coma, it's also a relatively good fit. We have somewhat the other problem here that we overestimated on average. And I also overlaid the MTNG line from Rüdiger Packmore's paper from like 2 years ago. So it's actually a very good fit to MTNG overall, despite the fact that our simulations are a little bit less, we have a little bit less resolution compared to MTNG, but not much. Consistently, we are off though in the outskirts. And we are off in the outskirts by almost a dex. Our best working theory that we haven't tested yet, and that's where we like really want to thread the needle to come together with the AGN feedback group, is that there is a possibility of, by having a more efficient AGN feedback model, redistributing mass from the inside to the outside and actually lifting that profile up a little bit. That's a very natural way forward in collaboration with the black hole working group. Okay, so let's find coma. So now you can obviously try to play the game and find the clusters who best fit that data. You immediately see that there's like almost this problem remains, right? We find in the X-rays some very, very good fits all the way out to the outskirts. Then we have a few that really undershoot. But the reason they undershoot is because they're actually very good fits in Compton Y, right? So we use the combined criterion here. So that's nice and not nice at the same time. I would have wished that like there's like 1, 2, or 3 clusters that are bang on. But that's at the same time, then we're done, right? Then we've like understood that object. There's not much more to do. So we have to figure that out in a little bit more detail. In any case, here are our 10 analogs. It's cluster 36, 13, 2, 22, 23, 11, 0. That's my favorite one. So that's the main reason why it's like we need to do at least 8, because that's the 8 best fit. And then 34 and 28. And I'm showing these in the kinetic set mainly because it's not so interesting for coma per se, I would say, because that's not one of the clusters that the KSZ is super interesting for. But it's the same line integral convolution I needed to test my tool, just with a different quantity, right? That's the main reason why this is there. All right, but there's definitely interesting science cases for some of the other clusters in relation to KSZ. Perseus would be, for instance, one of them, which we also plan to, simulate down the line. So now let's look at their masses. So this is now the blue line here is basically the distribution of masses in M200 crit. And the first thing, just ignore the dashed lines for the moment. That's all the cluster masses that we have simulated. That's where they fall in this diagram. The first thing that you can see is that the peak of this is nicely traced by the dark matter only simulations that Stuart did, which he will also talk about after we're done here. And that's quite promising. So we have even more confidence now that this is coma, right? And we selected this correctly. It's a little bit to the left. I'm not super surprised that this is shifted a little bit to the left, because you tend to be always a little bit less massive than target based on my experience in cluster zoom simulations. So I'm not super surprised that we're not exactly matching that peak. But yeah, it works. All right, now we scatter a little bit all over the place in M200 grid, unfortunately. So my hope before making this plot was that they would all be like, very tight around that peak. They're still like somewhat tight around that peak, but not maybe that great. The picture changes a little bit though if you look at M200 mean. Then you get actually like 3 clusters at almost the same mass that trace that peak that also match the X-ray and the Compton Y quite well. That kind of makes sense, isn't it, right? Because M200 is these clusters follow mass conservation, right, to a degree. So the larger the sphere of influences that you look at, the more likely it is to actually trace that peak with the ones that we matched. But yeah, the most of them, so 3 of them trace that peak, but all the rest of them lies to like lower cluster masses. So I think if we combine that, we definitely don't want to be more massive. I don't think we want to be in that end of the distribution for coma. Yeah, same story for M200 top hat. It's just like, I don't know what included this, just want to see where the peak is. There's like 3, it's the same 3 that trace M200 mean quite well for the peak as well. And then you can look at M500 crit, and there's like 5 clusters that scatter very nicely around that peak. So if you look at, so it's nice. Like it's again the same 3 that trace the peak here quite nicely than the 3 that trace that peak quite nicely. You can understand that when you look at the 6. So from that you get 6 clusters that are maybe favorable for resimulation at higher resolution, which are these 6. You can also understand by looking just at these pictures why they maybe trace the distribution peak very nicely in M200M and M500 grid. Because this is M500 grid, right? It's always this cluster center. And then it just depends a little bit whether your companion is a little bit outside, like here, or if the companion falls inside, like here, right, into M200 mean, where you lie in that distribution exactly. All right, I think that's already quite successful for 6 months of work. We have 50 simulations completed. We learned a lot. It's a first try. So the simulation folder is called first try on my Scratch, which I'm personally very proud of because I actually labeled it first try when I started. Yeah, I think we need a second try for a number of reasons, though, and that's what I'm going to talk a little bit about. So the things that we learned from this so far. So the first thing to say is like galaxy cluster zooms are always a bit iffy, mostly because their Lagrangian infall region is so big. And you get a lot of substructure at high resolution. It's just not there at low resolution when you run the parent. And it's a little bit related to, they were not quite happy right now that our parent is relatively low resolution. So we would like to have a little bit higher, possibly 512 or 1024 cubed for the parents, that we can do a little bit more sophisticated reconstruction of the Lagrangian region of the cluster. Because at the moment, we just don't have the mass resolution to do like a merger tree tracking, for instance, of substructure. Of course, these also, so we struggle in some of the runs. In many of the runs, we're okay with like low resolution intruder particles, but some of them suffer from some, 0.01% of the total mass in intruder particles, which we really don't want there. And that's something we have to work on. So we have also a computing time and storage constraint. We're at 16 terabyte right now and spend 5 million cores for these. For the full set of all the clusters that we want to do at that resolution, we need 224 and 70 million. ideally 500 terabyte if we want to write a few more snapshots. And for the high resolution ones, we need 24 million CPU hours and 50 terabyte of storage. It's just like how things are. And a possible better solution for this than we're doing it right now would be to combine it with the new multi-zoom technique that Volker had added to NGenIC. And this is exactly where I want to spend like 2 minutes. Shai is going to spend a little bit more time on this maybe later, talking about the roadmap ahead. So Volker has spent a lot of time the last couple months to get like a multi-zoom setup ready to go, which we couldn't quite use yet for the simulations we did, mostly because we needed music's capability to read that constrained IC file, which is not yet in NGenIC, which is some functionality that I want to add over the next couple weeks and months. So Volker's code, though, can do something very, very cool because it can select different target halos in a large-scale Cosmo box. Here it's a 200 megaparsec over H box, and have multiple zoom regions around each target object. And it's tested, it's implemented, it works with 2LPT in our repo 2 and then Gadget 4. And yeah, there's also legacy support for some of the boxes that the TNG collaboration has done in the past. And just to show you one of Volker's efforts from the last couple months, this is what you then get. So this is what you can simulate with this. You basically can sample from like a halo mass function and simulate that select halo mass function and obtain like some stellar mass function, right? And yes, so this is where we are with this. Obviously, it would be very nice to add the capability of reading these constrained IC files for our cluster zooms, because that makes data handling a little bit easier. And we could do them in one go for all the local clusters that we're interested in, not just Coma. And it's just like makes data handling a little bit better. And I think with that, I just stop here. And I think we're happy to take questions now.